Thank you very much, Siwei. Clarification, my bachelor's and master's were at both at UT Austin. And then my PhD, it was a mix of MIT and UIC, and I was based in Chicago the whole time, so I decided to stay in Chicago. So let me share my screen. And this is actually, the presentation I'm giving today is based on my dissertation. So, okay, I have it in full screen, and just let me know if there are any audio or video issues. And Chicago is having an air show put on by the U.S. Navy tomorrow, and they're practicing right now. So there's a little racket from time to time, but hopefully that won't distract from the presentation. So my dissertation thesis studied the topic of strategic decisions in agent-based freight transportation models, looking at methods and data. And first I'll introduce this topic and motivate it. Then I'll briefly cover some previous studies, and then go through the main elements of this work, which were kind of unified in within the thesis. First, there was an agent-based framework, really developing a behavioral architecture to model the movement of goods through supply chains. And then I look at strategy data, because this is a huge gap in the literature. And I come up with some methods to measure attitudes using natural language. And then I show how to model strategy in a behavioral framework, which links strategy with strategic decision making. And then as a case study, sorry, I didn't realize these were on. These timings, I think this will work. Okay. And then I look at the impacts of strategy very concretely, tying strategy to what do transportation emissions and energy look like. So just to introduce the topics, first of all, what do I mean by strategy? A strategy is, I define here as a latent or unobservable objective that a company adopts, and a strategy lends consistency to a company's decision-making processes. This is referred to as strategic alignment in the literature. It can be represented mathematically as a latent variable because we can't observe it, not very well anyway. And it informs outcomes that are observable to and measurable by analysts. So in other words, there is a way to kind of quantify it, but we need to use some latent variable techniques to do so. A strategic decision, on the other hand, is I'm defining as a manifest or observable outcome of a decision that an individual company makes. And a strategic decision then is basically an action or a decision that is based on strategy as well as other factors. There are many impacts of freight transportation. Some of them are, freight transportation is huge. It impacts mobility with, just billions and billions of time and fuel wasted annually due to truck congestion, auto congestion as well, but trucks have kind of an outsized impact on congestion. It affects international shipping emissions and just emissions in general. For example, carbon dioxide impacts are comparable to all the pollution that's emitted by Japan for international shipping. And strategies also impact energy emissions and mobility, looking more at the, say, a national level. And I look at a case study later in this presentation that talks about the strategy of producing SUVs in the US and shifting production of smaller vehicles such as the Ford Focus to China. And that's where I quantify some energy and emissions impacts. So the thesis of my dissertation then is that strategy unites decisions that individual actors make, actors in this case meaning mainly firms, but there are also implications for households or passenger models, And that this kind of consistency or unified decision-making can be achieved in agent-based models through a carefully constructed framework design. I'm also proposing that strategy should be integrated into the model stream in a way that permits or even enforces consistency between longer term high-level decisions and any number of other long-term, midterm, or even short-term decisions. So my main objectives here are to develop the conceptual frameworks, the mathematical models, the data sources, and proof of concept applications that operationalize these ideas. So it's really kind of an all-in-one kind of thesis. And this shows graphically the contributions that I make with this work. So I have this conceptual modeling architecture where I show how strategy can be used to unify decisions in this framework. Basically, it involves developing and understanding strategy in this long-term strategic layer, and then feeding that into the shorter-term decisions. I developed methods to develop the strategy data using natural language, which is much easier than conducting surveys, and also develop a methodology for modeling strategy and strategic decisions. And there are joint and sequential aspects in the decision making that you'll see later on. I do look at two different types of applications in this work. The first one really focuses on transport and logistics strategies. And I mean, think of it really as outsourcing. You know, do firms decide to outsource these functions, or do they have them internally? And I look specifically at fleet ownership and distribution center control, whether or not the company owns or leases its own distribution center space. And then the final case study is the one that looks at the sourcing strategy and specifically at automobile production. So there are a lot of previous studies that relate to this in terms of theoretical foundations. There are there are different categories of firm decisions or household decisions or passenger decisions, and a three-layered construct is routinely used to model these.
Excuse me, Dr.
Yes?
Stinson, there's a question from Professor Ricci. Does population synthesis refer to the population of trucking firms and fleets?
The population of any establishment that is involved with freight transportation. So both shippers and receivers, so more the trade agents as well as the carrier agents. Yeah, thanks for that. So there's a strong precedent in the literature for using a three-layered framework for firm decisions or household decisions. And then in terms of strategic behavior, there are a lot of theories around that, looking especially at, say, how do people or firms form a plan or strategy that's maybe it's latent to everybody else, but they know what their plans are. What we see then is the action. We see the strategic behavior that comes out of this plan. And there's a lot of literature in this area in economics, transportation, and so on. I also, my work is also informed by joint models and look at how to relate latent and manifest choices. Factor analysis, structural equation models, hybrid choice models, all inform this work. And the type of data and models that I talk about here are generally in that in that domain. And then the two-stage choice process, which is a sequential way of looking at choices, also informs this work. So, and this was Mansky in 1977 was kind of the major leader in this area, where he proposed that in stage one, people or businesses may form a choice set. And so they, and a way to do this is by thinking what kind of parameters they're using to generate their choice set. And then finally, they have their choice set. And then stage two, they make their choice. So the work I'm doing, you'll see fits with this as well. And then in and sorry, some of the headings got a little smushed. I'm on a different computer today. In the computer science area and really in computational linguistics, a whole stream of research has emerged in how to quantify symbolic data. This had its origins really in the 70s and 80s, but really took off in more recent years when natural language processing applications were developed to harness these concepts. And the idea here is to look at symbols such as words as in terms of a distributional representation, where so here in this very simple example, there are two dimensions, mobile and alive, and the nouns that I've shown here can be categorized as kind of a mix of the two. So it's sort of, it's a way of reducing dimensionality of large databases of words, and then that will be come up in my work. So the behavioral framework, the architecture that I've developed, which as Siwei mentioned is called Crystal. I'll talk about this now. Briefly, the state of the practice in agent-based freight models is there are several of them. Most of them that are around today sort of originated in the aggregate, disaggregate, aggregate framework of Gerard de Jong and Moshe Ben Akiva. And that has had many variants that have been implemented across the US and internationally. There are a couple of others that are similar to that, but maybe one step removed. One is SimMobility in Singapore, and the other is the SWIM model in the, I believe it's the state of Oregon. And then there are some that are frameworks only. And really, if when you look through these, you'll see that strategy is just an enormous gap. It's none of these really look at strategy at all. And then I try to address some other areas like, none of these predict, make a fleet prediction for the firm agents that are in the models. In some cases, they simulate them, or they do what is often done in travel demand modeling, which is assume that anytime a shipment needs to be made, a vehicle is there. And then I also add a push-pull boundary feature to, which is really a major impetus behind, like, say, just-in-time versus economic order quantity modeling. So that's another innovation, and I won't go into too much detail on a lot of these because, but feel free to ask questions, or I can refer you to others, my written sources. So the framework is organized, as I mentioned, in 3 layers. The strategic layer has trade strategies, logistics strategies, supply chain and distribution networks forming. The firms select their assets. They choose locations to place their establishments. The tactical layer is where each firm estimates how much goods it will need. They form partnerships with each other. They make orders for goods. That gets converted into shipment rosters and vehicle tours. And then finally, in the operational layer, the vehicle tours are routed on the network. And we can estimate things like vehicle miles traveled and travel times. So the framework that I've named my framework as Crystal, which stands for Collaborative Informed Strategic Trade Agents with Logistics. This is the full framework. Again, just in the interest of covering other things, I won't go into too much detail. But a lot of it I've already, I, along with support from my team at Argonne, I've implemented a fair amount of this, and I'm in the process of developing models for some of the other pieces. And as you see here on the left side, I want to bring your attention to the gray block that kind of shows how the strategy model produces strategic decisions, these very high level trade and logistics decisions, as well as choice set parameters. And then these are used to inform these lower level processes in the model. I submitted in 2019 a prototype of this to ABM Trans. Just to brag a little, it won Best Paper Award. Again, this is based on my dissertation slide, so I had to impress my committee with something. And then this slide shows how it really highlights how I integrate strategic decisions with the rest of the framework. And this is the strategic alignment that people talk about with firms and businesses, but really this could also be used with passenger modeling. The push-pull boundary aspect is actually a pretty interesting and unique feature of this framework. So the agents in the model, they forecast the amount of demand that they'll need, and they purchase inputs to support their production. And then we have a trigger set up to model the visibility that they have of downstream demand. And if they have, say, full visibility, then they produce their outputs when they get their orders. So in that case, they use a just-in-time kind of shipment size method, whereas the other more typical way is they don't know what their downstream demand is going to be, and so they have to predict what it's going to be, and they end up using an economic order quantity model for that. And that's called the EOQ model, and it actually includes some buffer inventory, so that in case the firm runs out of goods or whatever, they'll have something to sell. And that is used then to generate demand for warehousing, for an on-site warehousing space. Another feature that I wanted to point out with my architecture, is that I have both firms and establishments represented. The literature, you'll hear a lot about firmographics, and really they're talking about establishments. The reality is no one models firms in the transportation literature. Everyone's modeling establishments. The issue is that many establishments do belong to a firm. So an establishment is a single site, and the firm is the collective. So for example, McDonald's is a firm with I think 14,000 establishments across the US. Now this could lead to issues with downstream if, say, McDonald's establishments are picking some sourcing agent, and they pick, say, a distribution center that really serves, say, Target or whatever. So it's important for just consistency in the model. And then things like fleet ownership, locations, those are often decided at the firm level rather than the establishment level. So just fundamentally, the framework is constructed around firms for this reason. I'll just breeze through this. Okay, then now I'm going to tell you how exactly I'm getting strategy data, because strategy, it's hard to understand. Businesses may talk about it, but it's not like there's some strategy database out there that says this company has strategy X and it's measured at 9.5. Like, there's nothing like that. So we need methods to get this kind of data. And I've developed a couple methods using natural language data. I'll just go through this. There is a historical precedent for using natural language-based sources. There are things like Twitter and sentiment analysis, but that's not really suitable for something that's more like rational decisions, like concrete, like strategy. Bag of words has been used with supervision. It has been applied with in an unsupervised way to in the psychology domain, maybe in some other domains, but it, you know, to my knowledge, it's very, very infrequently used for as strategy measurements. So that's one of the approaches that I look at here. And then I develop an entirely new method, which combines natural language processing and principal components analysis. And I generate unscaled attitudinal measurements, which I then use as firm attitudinal data. The methods that I'm going to talk about are called the bag of words with simple scaling, the SSBOW, and word to vec PCA, which is called W2V PCA. I'll probably just say word to vec PCA. I created a Python-based attitudinal data development engine, which I call ADDIE. It compiles input data, processes text data from establishments and or firms, and then develops attitudinal measurements. And I develop also a proof of concept to show how well these work. And I look at Fortune 500 companies in freight intensive sectors, and then use these attitudinal measurements to detect firm strategies. Now, the main hypotheses here, and the first one is the bag of words hypothesis, which is this is also it's called the bag of words hypothesis, and that is that people or company will use certain words more or less frequently, or they may use them differently in different contexts or with different meanings. So the second hypothesis is called the distributional hypothesis. And really what's unique with what I'm doing here is that I'm kind of bringing them in these hypotheses into a different context, which is generating strategy measurements. And I empirically test these hypotheses on my text data using some pre-selected keywords. So now I'll talk about how the SSBOW algorithm was developed. It's very simplistic. If you've used bag of words, then you know that normally you count up the number of times a keyword appears in a document, and then divide it by, say, like the total, some kind of total. Here I'm looking at the total counts of all keywords in the document, and then I come up with a measurement between 0 and 100. So it's these are kind of scaled in the sense that they're constrained to be between 0 and 100, but their relationship of the measurements to each other are not really scaled. I mean, they could be infinity, or for all practical purposes, infinite. The development of the word to vec PCA algorithm is, this is how it goes. This one's a little more elaborate. So the idea is that companies will have different goals and different strategies to support those goals. So their reports will be different, or their letters to shareholders will be different. And so they'll use words in somewhat different contexts. So for example, if we have a company number 1, which has a strategic focus on product development, versus company number 2 that has strategic transportation and delivery focus, transportation or company 1, I mean, if they're using the word reliable, maybe they're using it to talk about the reliability of their products. And company 2 may be talking about the reliability of their delivery. So I really wanted to see what would happen, if I brought in some context information to measure what the company is, how the company is using those words. A little background on quantitative analysis with words. Words are often represented as vectors in the computational linguistics and computer science areas. Before the 2000s, the typical process was to assign a so-called one-hot vector to each word. And this is kind of how it looks, so words like container or bin, they'll be different vectors, even though they basically, mean the same thing. One problem with this is obviously, the orthogonality of vectors for similar words, but then also dimensionality can be enormous because there has to be one dimension for every unique word in the vocabulary. So what Word2Vec does is, Word2Vec was developed by Mikoloff and colleagues in 2013. And this algorithm, basically you input the each word in the vocabulary in its one-hot vector form, and it estimates a weight matrix, which compresses compresses that those vectors down into the vector h, which could be maybe 100 dimensions instead of 10,000. And then it predicts the identity of the missing word in a context. So yeah, sorry, I should have mentioned at the start. You feed in the context words, the one-hot vectors of the context words, and then the goal of the algorithm is to predict the identity of the missing word. So that's how the algorithm and its solution are structured. But really, what we're after here is this first weight matrix WX. Because this then is sort of as a post hoc way, it's used to convert a single one-hot vector word into a much denser representation of that word, say a 100 by 1 representation. And it turns out that Word2Vec uncovers, this process uncovers a mathematical structure among words. Here, there are some example results that are visualized with principal components analysis. Instead of showing, we can't show all 100 dimensions, but let's show 2 and see what it looks like. And this is what it looks like. So the word for queen in this representation is roughly equal to the vector of king minus man plus woman. This is a very famous example. So what I do here is, again, my goal is to see how are companies using different keywords differently? Are they using them in different contexts? Is one really talking about reliable products and the other one's talking about reliable delivery? Because if so, then we don't want to treat reliable as if it's, means the exact same thing to every company. So what I do is I identify a set of keywords that I want to look at, and I tag them. And then, so by doing this makes the vocabulary grow by, well, the number of companies -1. And then I apply Word2Vec to this data. And then as a result, I see I obtain the vector for those words that is specific to how each company uses it on average. So if company 1 is talking about reliable products and their products are so reliable, they're going to have one vector, and another company that's talking about, oh, we have this fleet that, it's so reliable, blah, blah, blah. And, they're always talking about it in a transportation context. That's going to be another vector. And then, but then the question is, we have these vectors, but do we measure their similarity, or, what's the best approach? So what I do here then is I apply principal components analysis to each vector, and then I project those onto the dimension of greatest variance. So I just, I use the first principal component and, project these vectors onto that. And then these become what I'm looking for. These are the attitudinal measurements, or the strategy measurements of companies. And so companies that are, excuse me, presumably companies then that are using reliability mainly in, say, the transportation context, they're kind of maybe going to be all the way on the right here. Companies that are mainly using it in the product context are probably going to be, all the way on the left here, and so on. So these are the measurements that I take. This is just a sketch of the data development of the ADDIE tool, which I won't go to in a lot of detail, but just to say that, the process that I developed it's data driven. So, the attitudinal measurements are generated with the text data. And here I'm going to use annual reports that are filed with the Securities and Exchange Commission, the 10K reports. But then I'm also using data on their actual fleet ownership, whether or not they own a private fleet, and their distribution center operations. So then in a proof of concept, I look at 241 companies total from the Fortune 500. These are all freight intensive companies. On average, 61 firms have, so about 25% have trucks of some sort. They have a fleet. Most of them have heavy duty trucks, some have medium duty. I'm sorry, all of those have medium duty trucks, and most of them have heavy duty trucks. About 209 have either own or operate their own distribution centers. And I've gotten the characteristics of all of their distribution centers from a CoStar real estate database. On average, they own 14 distribution centers. So I have, data on their total square feet, mean size of the distribution center, standard deviation in size of the distribution center, as well as some characteristics that relate to population, like the mean distribution center square feet per person in the population. So this kind of gets at to how dense are they, where are they locating their distribution centers? And then how close are they to rail, truck, intermodal, or major water ports? These companies are mostly in the manufacturing sectors, but there's also a lot in the retail, wholesale, as well as petroleum, gas, and food products. And then I used a couple different keyword sets. The first one is, I'm using the word attitudinal here. These are kind of like fuzzier keywords like value, quality, things that are a little harder to describe in a concrete way. And then I have a 22-word mixed keyword set with attitudes and some more concrete logistics terms like transportation, national, and so on. And this just gives some example. Okay, so then the results then, first I'm going to show the SSBOW measurement results. And the left side, it really shows like there are some differences, some words like affordability and diversify, they're hardly used, whereas words like value and costs are used a lot. I made some histograms, like looking at whether they have distribution center control or not. Yes, there appear to be some differences, but this is really like, it's really hard to tell how important their differences are by looking at that. So I'll show some more valuable comparisons next. But first, results for the Word2Vec PCA. So here I did get very nice results, and with this actually, so what I showed you with the setup in order to use the measurements in, say, behavioral models, I would tag each word with a company tag. But here I wanted to see, okay, what about companies that have a private fleet or not? So on the left side, I grouped all the documents where the company has a fleet, and then those have, say, reliability _F. Without a fleet means just plain reliability. And so you can see this is actually resulting in different vector estimates for reliability, efficiency, and so on. And I did the same thing with the distribution center control and found a pretty similar finding. This shows then the spread in the measurements, and here the companies are the keywords are tagged on this slide for every individual company. And this shows how the measurements really they're kind of naturally scaled. So however they're using the words in context, like that's basically their scale. And so some of these have, maybe it's hard to say, I think it needs more interpretation, but some of these companies seem to have some of these words seem to be used in a more confined set of contexts, whereas others may be used in a more broad set of contexts. And then on the right side of this, I show the percentage of variance that is explained by each of the by the first principal component for each of these. I'm going to skip this one. So then which one's better, right? I mean, bag of words or word2vec PCA. I'm not proving one is better than the other here, but I did do some testing of differences in means, and then I did some factor analysis. And here I'm showing the differences in means where basically, again, looking at group means of say DC control versus no DC control, fleet versus no fleet, and then seeing if the method picks up a statistically significant difference in the two. And I used a t-test to determine this. And bottom line here, the verdict's still out. It seems like, based on looking at differences in means anyway, that it's hard to say that one method is better than the other. I also looked at the number of variables with significantly different means, just counting them up, and it seemed to rely more on the which set of keywords is used. So it's not really a great result. Like, I mean, bag of words seems better with one set of keywords, word2vec seems better with another. The factor analysis, though, the confirmatory factor analysis was a little more insightful because actually the product and delivery, sorry, back up a step. It did yield some statistically significant more relationships with word2vec PCA more than it did so with bag of words. With both of them, actually, though, I identified two latent strategies, being product focus and delivery focus. And the keywords that you would imagine being lined up with those are, they lined up with, so words like innovative, quality, security were aligned with, what I'm calling the product focus. And then words like efficiency, reliability, technology, and service aligned with delivery. And, just you can just see, the word2vec PCA, I think 3 stars, I think I denote as 99 percentile significance. And you can see the word2vec PCA definitely appears to be performing better than bag of words here. So, okay, I have about 15 minutes left, so I'll go quickly then through the behavioral model of strategic decision making and probably kind of skim through some details just in the interest of time. So the going back to my goals, I wanted to develop a model that takes strategy and other variables as inputs and then estimates, predicts strategic decisions. Some of them being, say, discrete continuous, some of them being more choice set parameter type decisions, things that could be used, downstream in the model. So there's a latent variable strategy model as well as a joint model of strategic decisions as part of this. Briefly going through the literature, there are a few things that could be used for this, but nothing's really been designed for this use, and certainly doesn't, to my knowledge anyway, doesn't, nobody's talking about this in the model stream using one of these more elaborate joint models. So with my model, I predict high-level decisions, latent variables, multiple discrete continuous decisions, and choice set parameters jointly. And again, here's our population of agents. They select a strategy bundle, let's say, and then this produces the strategic decisions as well as choice set parameters. Really the contribution here is, there are a lot of joint models out there. I mean, Chandrabhat alone, he was my master's advisor. He has probably, 30 unique models that do everything. But actually, one area that's not used very much in transportation literature, behavioral models, is the seemingly unrelated regression model that how Audrey Fong, she's developed some work in this area. I think with David Brownstone, who I think may be here. But her work, let's see, what was the difference here? Yeah, so I introduced latent variables into the Tobit seemingly unrelated regression formulation, and then use that to estimate all of these. And this is what it looks like. So on the left, we have the attitudinal measurements, really indicators, if you will. And these are what's produced by Word2Vec or Word2Vec PCA, or maybe an attitudinal survey. Then we have our strategies. These are the latent variables. We have our other exogenous input data, and then those feed into some latent joint decision propensities, and then those feed into the strategic decisions choices. And the way it's set up is there's sort of a set of decisions, which then combines, the continuous and discrete features, which was, I think, a really nice aspect of Fong's work. Okay, in the interest of time, I will skip through the math and just kind of go through the highlights. So there's a structural equation to represent the latent strategies. There are the measurement equations, which relate the measurements to the unseen strategies. And then we have a set of observed yet truncated variables, such as owns a fleet versus doesn't own a fleet, or say how many vehicles does are owned. And then, well, I'll provide some references and you can read through it. So the way to set this up would be, creating the integration with which shows the probability of selecting a strategic decision based on all of these unobserved strategies, as well as observed factors. And typically the way this is solved in the transportation literature is with, say, maximum simulated likelihood, or the, Chandrabhat has used the maximum approximated composite marginal likelihood, the MACMAL approach. But there is another approach, which is using hierarchical Bayes, and using Gibbs sampling, which was developed by Albert and Chib. So here you establish some prior distributions for the unknown variables, parameters and so on. You form an augmented posterior, and by augmented, the nice trick here is even though you don't have you don't have data on the unknown strategy, but you generate a data point for some unknown strategy, and that is the so-called augmentation process. You go this through a set of iterations, maybe 10, 20, 30,000 iterations. And if something can be made closed form, you do it, and then you end up solving the parameters for this. And so then what you have then is the set of parameters that you can make to then plug into the model to do some predictions. Then I developed an application using this model and took measurements of words like customer, delivery, efficiency, and so on, using the Word2Vec PCA process. I've similar to the factor analysis earlier, I found two underlying strategies, one for customer service and the other one for logistical sophistication focus. I had these other exogenous inputs: market value, profit margin, industry, and revenue. And then I had 8 different variables, strategic decision variables, things like number of heavy duty trucks, number of medium duty trucks, total square feet of distribution center, mean square feet of distribution center, standard deviation in size. And so, I mean, you can see already, like, all of these things relate to location preferences. Like, what do companies look for when they want to get a distribution center? How big should it be? What range of sizes are okay for it? What's the density of population, the proximity to rail, to ports? And so the reason that it's useful to treat these as latent, even though they are observed in a censored kind of way, is that, for fleets that, companies that say don't own a fleet, you can, think sort of like as how close they are to, to the verge of owning one. So you can think of it as a continuous distribution, but it's just truncated, because if they don't own a fleet, then we actually don't observe what they're doing, or like we don't observe their propensity, rather. Okay, and so here are the results. The next few slides show the results of the model estimations, and the customer service focus strategy variable. The words customer and service, literally just kind of jump out. And the other words some of them are significant, like delivery and efficiency is kind of borderline significant, but that shows that, or rather it's, it kind of lends credence to the hypothesis that, okay, some companies are really focusing on customer service as a strategy. Other companies seem to be focusing on logistics as a strategy. So, I mean, like Amazon's a great example. They put a lot of resources into figuring out how to make their distribution most efficient. And so we see the words like that jumping out as well: distribution, logistics, transportation. And then I also applied as part of the model output, we estimate strategic decisions. These are the strategic decisions for medium duty and heavy duty trucks. And really what this shows is that the disposition to owning a fleet and to even owning a larger fleet grows as revenue increases, and for certain industries in particular, the food and beverage and petroleum and gas industries. And then the customer service and logistical sophistication, they did seem to have some impact on this, but it was fairly small in terms of significance. The strategic distribution center control decisions were also fairly intuitive. Higher revenue companies tend to have the largest distribution centers. There's a lot of variability of size in the manufacturing and retail wholesale sales sectors. And here, actually, the CS and LS, are 2 strategy variables. In general, they were fairly significant, compared to the fleet ownership decision. So, higher CS and LS scores, for example, meant that the company has less distribution center area, kind of a lower footprint of distribution centers, and their distribution centers are smaller, and so on. And then some of the accessibility variables also were, they were very, they had nice results. They showed, say, firms that tend to locate their distribution centers near intermodal facilities or water ports. Those tend to be manufacturers, and especially higher revenue firms. So, these are probably firms that are engaging in global trade. These are huge firms, almost certainly multinational in their own operations. And so having distribution facilities near major ports or intermodal facilities just makes sense for them. I did some validation. It looked good. It was, comparing within the data set, though. It would be better to compare, outside of the data set. And then, I'll wrap it up in the next few minutes. But just wanted to show then how does this inform the rest of the model. So, with this model, I'm predicting medium duty and heavy duty truck ownership. So this would be used, say, to feed into models of truck tour formation within an agent-based context. Characteristics like total square feet, average population density, and mean square feet of distribution centers, those would feed into an algorithm to, say, predict national level distribution center structure. And then the other variables, mean square feet, standard deviation, distances to intermodal yards and ports, those then become choice set parameters for a more detailed location choice model. And here's an example of, what it looks like. So the company, we simulate the nationwide distribution center for company C on the left side here, and form its strategic choice set. So this company is looking for, say, distribution centers that are on average maybe 650,000 square feet, plus or minus 150,000 square feet. Maybe between 5 and 15 miles of intermodal rail. And then that information is used to generate the choice set on the right. So if I'm building a detailed model of the Chicago region, here's my company, it has some locations in Chicago. What kind of locations is it going to consider? And here, here are some candidate locations and, where say like intermodal truck rail yards are, and we'll have the characteristics of the properties and so on. And then, in accordance with the two-stage choice set or the two-stage choice paradigm, the company makes its final choice, maybe say like a logit model. So I'll quickly go through technical contributions, and then, just briefly, I did like a smaller case study to show like really what are the effects of business strategy, and this gives some real world estimate, real world data, and then my estimates of their the energy and emissions results or outcomes of the shift in Ford Focus production from Michigan to China. So this really shows, like, this was kind of a sketch level exercise done mainly with spreadsheets. This was done earlier in my dissertation process, but really what it shows is the let's see, we have the Ford who, Ford, they want to produce SUVs close to the main consumer base, which is in the US. They think that trend is going to continue for many years. So that's the strategy part. They're banking on some unknown future thing, and they don't quantify this. They're just saying like, this is what we're going to do. And so they end up shifting the production of the Ford Focus to China to make room in the US factories for more SUVs. And here I quantify, I looked up a bunch of rates for energy and emissions and quantified that, okay, yeah, this is a strategy that's impacting their strategic decision to actually produce somewhere else. And it has, as you would expect, enormous consequences for carbon dioxide, sulfur oxides, NOx, PM10, et cetera. Now, I didn't quantify the secondary effects, which would be, of course, producing, say, the SUVs, instead of producing them in China, now they're being produced in Michigan, so that saves some. So that would be, a next step for this work, but it does show that they're, strategy does impact ultimately energy and emissions. So yeah, in summary, there's the framework, there's the data development processes, the model, and proof of concept. There are some limitations and extensions. So I guess just to highlight here, methods for keyword selection could be improved. I really just used my judgment on these, picking what was most seemed reasonable to me based on the transportation literature. Certainly more rigorous methods to compare or to really like compare different approaches, even like bag of words versus words with PCA versus attitudinal measurements. Is there a way to compare the outcomes mathematically? And I think there is, but that would be a good next step. Yeah, then I'll just skip through these and yeah, I think, extending these methods also to passenger models would be a really nice extension. There's been, you see the word talked about in the word strategy tossed about in the literature sometimes, but I think it would be nice, great to see it in more in a framework like this, and some acknowledgements, and then yeah, if you want to look at any references, I'll share the slides with Siwei after this, and you can refer to those. So thanks again for having me. This was great to talk about my research with you, and I would like to open it up to any questions now.
Well, thank you, Monique. Thanks for a very interesting presentation and the excellent slides. I'm first going to stop the recording, and then we could get to the